Okay, so 4/6 is called the natural base e. So basically we're going to be dealing with exponential functions with the letter e in them. And e is just a variable that represents a number. So if you think of like pi is an actual number, right? But we use a symbol to represent the value. Okay, e is the same kind of a thing. So e itself is 2.718281828 and so on and so forth. Okay, it's just a letter that represents a value. It's called the natural base. And if I put it as f of x equals e to the x, I'm now taking a number and raising it to an exponent. So it's an exponential function, but we call it the natural exponential function because e is a natural base. So a lot of this can be treated exactly like we did with exponential functions, where if you had a number and you raised it to an exponent, you are plugging values in, this kind of stuff. The difference is that these you will use your calculator for. I'm not going to ask you to raise 2.718281828 to a power anything other than 1, really. So you'll use your calculator to get the points that you'll then plot on a graph for this kind of stuff. It has the same characteristics as the graph of any exponential function. So because it's just like writing 2.7 to the x, if I had 3 to the x, the higher the value, right? It would increase at an exponential fashion because 3 times 1 is 3, but 3 times 2 is 9, and that's a big jump. So it's really similar to the f of x equals 3 of x. It has all the same characteristics. The domain would be all real numbers because I can raise 2.7 to any exponent. And the range is going to be from y to positive infinity or greater than 0. I'm sorry, from 0 to positive infinity. Or y where y is greater than 0.
Yeah, greater than 0.
Mm-hmm. If I were to graph e to the x, I would take a, like a t-chart, plug in the values, plot my points, and you would see something just like this curve here, okay? So you're going to do the same thing we were doing with exponential functions in section 1, except that now your base is going to involve an e, so you're going to need your calculator. So when I go to plug these points in, you're going to want to simplify the exponent first, it's probably the easiest way to do it, and then get it to the point that you have to plug it in your calculator. So first thing is locate the e button on your calculator. So if you don't have a calculator with you today, start bringing one with you. You don't want to go to take a test on this stuff and not have a calculator. You cannot do it. Okay? I mean, I guess you could be superhuman and do it, but most of our brains can't do this stuff without a calculator. So can everybody locate the e? It's probably above your LN button. So if you have a graphing calculator, it's the third from the bottom all the way on the left. It's above the LN button. E to the x. Yep. So let's plug these values in first, simplify it, and then plug them in. So let's take -2 first. All right, so if I were to simplify this, this becomes e to the -4th plus 1. And then I'm going to type that in the calculator. E to the -4th. And I get 0.0183 and so on and so forth. Add the 1 to it. And this would be 1.01, which I'm going to obviously not plot exactly at 1, but a little smidge above it. You can, well, I just kept the 0, 1 because I have to know that it's not 1. Normally I would round to the nearest tenth. So it would have been 1. And then I go to the next one. So -1, e to the -1 minus 2 plus 1 is e to the -3 plus 1. Let the calculator do the work. E to the -3. Add the 1, and this time I get 1.04. So it's just a little bit bigger than that one. And then I would do e to the 0 minus 2 plus 1, which is e to the -2 plus 1. Which is 1.13. Actually 135, which is 1.14. And then I go to 1. E 1 minus 2 plus 1, which is -1 plus 1, 1.36. or 3/7.
And this is an exponential function?
This is an exponential function, yep, because you've got a base that's being raised to a power, right?
Okay.
And then go to 2, e to the 2 minus 2 plus 1. This is the only one you don't need a calculator for, because what is e to the 0? 1. And then e to the 3, which is 2.7 plus 1, or 3.7. And then the last one, 4. .38, which I'm going to round to 8.4. So I took each of them and plugged them in, and now I've got to plot those points. So -2 and 1.01 is going to be -2 and literally just a teeny tiny point above 1. And then -1 is a little bit higher, 1.04. 0, 1.14. 1, 1.3, so I'm getting closer to 1.5. 2 was 2, 3, 3.7, and 4, 8.4. So if this is 7, 8, this would be up here. So the good thing about this section is that it forces you to review the graphing of exponential functions, which was from section 1 and 2. Okay, remember that if the base was bigger than 1, what kind of model is this? Growth or decay? Growth, right? It goes up as you move towards the right. And because E represents 2.7, right, it should make sense that that's bigger than 1, or in between, or bigger than 0, which would make it a growth function. Does that make sense? Bigger than 1? Okay. All right, the natural log is a log with a base of e. So this is the same thing as saying log base e. And log base e, which is called the natural log, is represented by the letters ln. Okay? So when you see log base e, it's interchangeable for ln, and when you see ln, you can interchange it for log base e. They mean the same things. So if you look back on your calculator, the graphing calculator, ln is the actual button, and e is the button above it, okay? But they kind of pair together. God bless you. So all this means is if I were to find the log of base e, I can use the ln button, okay? Or I can find the log and change the base to e, and it's the same thing. But the one is interchangeable with the other. So we'll start to use some properties here, okay? So if I have ln of e raised to the 0.15 to the, times the power of t, obviously I can't plug this in a calculator because I have an exponent in that. I have a variable, sorry. So if ln is really the same thing as log base e of e to the 0.15 t, there's two ways to look at this. What happens if the base and the large number are the same?
They become 1.
They cancel out and I keep the exponent. Okay? What happens if I wanted to expand that? What happens if I have an exponent and I want to expand it? Bring it to the front. So this would be 0.15 t log base e of e, which is 0.15 t ln of e. So I want you to type ln of e in your calculator and see what happens. What do you get?
Wait, ln of e to the power of what?
Just 1.
Oh.
It would be the first part.
1.
ln of e should give you 1. ln of e cancels out. So you have two options. You can either...
I guess you won't.
Oh, you got to give it an exponent. So e would be e to the first. Yep. So you can, and hopefully this is the faster way, so hopefully this is what you remember. When you see ln of e, you can cancel it out and keep the exponent, okay? If you don't remember that, then expand it. Push the exponent to the front. Ln of e cancels to become 1. 1 times whatever that front number is going to stay that way. So hopefully this helps a little bit with mental math. Like if I look at this, actually let me go here first and then I'll go back up there. If I look at c, every time I see ln of e, I can cancel through it and keep the exponent. So this would be 2x plus this cancels x, which is 3x. Long way around, bring the 2x to the front. 2x of ln of e plus x times ln of e. And we know ln of e is 1, so this would be 2x times 1 plus x times 1, 2s plus x, which is 3x. So hopefully this is something, again, it's going to come with practice, but every time you see ln of e, you cancel it out and keep the exponent. If there's no exponent, then it's just 1. If there's an exponent, you cancel out the ln of e and you keep the exponent. Okay, now look at b. I've got a log in my exponent. So if it's 3 times a log, what can I do with that 3? I can bring it to the exponent. Good. So this would be up here as the exponent. So e to the ln of x plus 1 cubed. Now I can put this into log form. I can say this is log base e. And let's say I don't know the variable on the other side. This could be y equals ln of x plus 1 to the third. What is log base e? It's the same thing as ln. So I get ln of y equals ln of x plus 1 to the third. And then my one-to-one property says that the what I'm looking for, which is my y, would just be x plus 3, or x plus 1 to the third. Much faster is realizing that e to the ln cancels out, and what's left is my exponent.